Okay. So I'll restart because I was muted. So folks, this is the last lecture of the class. So I will keep it short, maybe 20 minutes or something. And after that, we'll turn it over for open discussion. And we'll have a recording of the formal part of the class, the first 20 minutes, the lecture. And after that, we'll have a discussion, which will be free form. So that will not be recorded. So let me just hit on this topic because this is important. And let's see. Uh, okay. So we start with a very basic observation. And this is really an observation not about any robotics task, but about human behavior. So it's well known that human behavior is hierarchical and has many levels. So the earliest example I could find of this in the literature was from this book from 1954. I mean, there is, in the AI literature, there's something called the General Problem Solver, GPS, which is like late 1950s and literature on planning. But I thought I found this book, which was about human behavior that they studied in like a small Midwestern town, just observing what people do. And there's this example where if you think of this like 7-year-old girl who's going to school, right? So you can think of first, if you think of the action at the second level of 1 second, A to B, she's stepping down from the curb. So imagine that she's walking from home to school. Okay. Then there is the action of crossing the street, right? Then there is the action, there's a bigger, this is a step in a bigger action, which is walking to school. Then, well, she wants to graduate from 3rd grade. Okay. That's so you need to go to your classes. And then there is a higher level goal, which is getting an education. And then as abstract as you can get, climbing to the top of life. Okay. But in all human activity and human behavior, we can construct these hierarchies. I mean, the canonical example that people use in the AI literature is about if I want to fly from here to Boston, if I want to go and give a talk at MIT, what do I need to do? There will be steps which are, me walking to the front of the building, taking an Uber, walking inside the airport, getting on a plane, getting off the plane, and so on and so forth, right? So we have activities at the lowest scale, which are the steps that I'm taking while I'm walking to the goal of walking out of this room and avoiding obstacles, to the goal of getting to an Uber, and we can continue. So there are always multiple hierarchies of action of human behavior. So when we go to a robot, it has to be the same. There is no choice. If robots are going to help humans, they are going to be helping us with various tasks, and all tasks will be hierarchical in nature. Okay. Now, how do we think about these tasks? So I have this slogan, which I like, which is action equals movement plus goal. So every action that you perform, we can think of it in two spaces. There is the physical space, I mean, the space of Euclid and Newton, where we are moving, and we move because we apply forces and muscles contract and so on. For a robot, there are motors which apply torques to joints and so forth. So there is the space of movements, right? Okay. But these movements are purposive. They are not random. They are in order to achieve goals. Okay. So one of the goals of that 7-year-old girl is to climb to the ladder of success in life at some level. I'm sure she's not thinking of that. She's probably just thinking of the fact that her mom has told her that she needs to go to school. But goals exist at all levels. The goals are hierarchical, and then the movements in order to achieve them are also hierarchical. But whenever you observe an action, always think of it as having a dual identity. There is the identity in the space of Euclid and Newton, physical movements, which translate to change in pixels and so forth. And then there is the more abstract story of what is this in the service of, and there's a plan and goal. And it's not one or the other. It's very important to note that. You'll often find people, you'll get into discussions where people are missing the point and they'll focus on one or the other. No, both are equally important, right? Okay. And this you can put in context by just thinking of the notion of planning and models at a more abstracted level. So again, I found this very old quote. This is 1943. This is even earlier than my previous quote. So this is from Kenneth Craig. And this is the little book he wrote, which is, if an organism carries a small-scale model of external reality and of its own possible actions within its head, okay, it is able to try out various alternatives, conclude which is the best of them, react to future situations before they arise, utilize the knowledge of past events, and so on. Okay, this is a description of the planning process, but it is because planning is thinking through what sequence you will act on before you actually act on it, right? You need to do some planning is what you do before you actually act, right? And that needs a small scale model of external reality. And now this term model can be interpreted in many different ways. I mean, there is the models of control theory people, which is essentially there is a state x, and x at time t plus 1 equals f of xt and u sub t. So u sub t is the control input you apply, the xt is the state at the previous time, and then there's some function which transforms it to the next, to the state at the next moment of time. And there are equivalent versions of that, which if you construct a linear model, then you can do ax dot equals ax plus bu. And this is where A is a matrix, X is a column vector, B is a matrix, U is a column vector, X dot is a column vector. And if you know the derivative, then you can, of course, go from xt to xt plus 1, right? And then often in this kind of a model, you have that you actually have some observables y, which are related to the state. It's not the complete state, but some observables from that. So these are, you should think of these as different mathematical formalisms, which are trying to get at the idea that Craig is doing, Craig is proposing. Today, there's a lot of usage of the term world models. I mean, which, for example, Jan LeCun has talked a lot about in terms of for vision, robotics, and so on. But it's exactly this idea. Okay, and this idea is a very good idea. It's fundamental. We have to have it. Okay, there's no. It's not like debatable. There are things which we debate, but this is not worth debating. This is just correct. The devil is in the details after that, right? What is the nature of the models? At what level of the hierarchy are they? How do we acquire them? We have to solve the learning problem of how do we acquire these models. All of this has to be done. Okay. I want to now get to this equation, action equals movement plus goal, but I'm going to talk about it in a different way, which is essentially about the role of words and the role of pixels. Okay. So, okay, so this is the book Harry Potter. I mean, it's been absorbed into all these LLMs. So in fact, you can ask any of your LLMs, ChatGPT, GPT-3, GPT-4, Llama, Gemini, whatever, you can ask it these questions and you'll be able to get those answers, right? So this is the level of language. Okay, but is language complete as a way of capturing the phenomena that we care about? And for me, the answer is when you watch this movie, I hope most of you have watched this movie, right? Is there anybody who hasn't watched this movie? Okay, I won't embarrass you. I assume everybody has watched this movie. Okay. Uh, because I had a young child, I had to watch it multiple times. So, okay. Uh, okay, and sorry. And this is the book, right? The book is not, and the movie are correlated. They're telling the same story, but they tell it in different ways. A great novelist describes things in a certain way with words. A great movie director makes the same story, but with pictures, with pixels. So there are words inside J.K. Rowling's book. Those are the tokens there. And then the tokens here are pixels, right? One is not superior to the other. They are both important. They're both important and they are correlated, but not exactly the same. That's why even after you read a book, you want to go watch the movie, right? Okay, now let's connect this back to this action equals movement plus goal. Of these, when you watch the movie, what is most obvious? The movement, right? The movements, you see them. The pixels convey the movements. So the movement part is much more evident in the movie. And if you are watching a movie with the sound off and no subtitles, you can certainly observe all the movements. What you miss out when you don't have listen to the dialogue are the goals. I mean, you can infer a lot of that, but it helps to have the dialogue. So the goal part is easier in language, because in language we can describe, like a novelist can describe the mental thoughts of a character. In a movie, Steven Spielberg can't show the mental thoughts of the person. He has to find a way for the characters to perform actions or reveal their inner state through movement, right? But both I'm trying to say 1,000 times, it's not one or the other. You need both. And when you think about approaches to robotics, you will need both. So people, when they say, oh, LLMs can do everything, they're missing the point, because language models are very good at capturing the more abstract aspects, which will be the goals and plans, but not necessarily good at capturing the movement. Okay, so let me now, with this background to set the mood, let me talk a bit about long horizon planning. And I've just like this one slide, I could have gone into more detail, but I think this is fine. So I want to do it as a little history lecture first. So the use of planning in AI, the earliest example is actually this GPS, this so-called general problem solver. But in the context of robotics is this robot called Shaky. Okay, and what you folks should do when you have the time is go to YouTube and search for Shaky the robot. So Shaky the robot was developed at SRI, so near Stanford, around 1969, 70, 71. And Nils Nilsson was one of the main people behind it. And in that project, they realized that they needed to solve the planning problem. And they came up with a formalism for solving the planning problem. And that idea has stuck around. And that idea is essentially to have operators which have some preconditions, delete lists and add lists. So there's a paper from like 1971 which has all of this. And let me illustrate that, and I will. The folks on Zoom will miss this because I'm going to use the board, and because I didn't have a slide for it. But let's do it for the people in the class. So the example that they used, that the Shaky robot, that they used for the Shaky robot was essentially about stacking blocks on a table. So you have some table, okay, and then you have some blocks. So think of this as little cubes. Okay, and let's call this block A and block B. Okay, so what do I want to achieve? And then maybe I have a third block. Okay, and let's call this block C. So there are 3 blocks on a table. And now I state my goal. And this was all done using predicate calculus, so logic. So the goal that was that suppose I have is on A, B, and on B, C, and on C, comma, table. Okay, so this is the goal. Okay, how do I achieve this goal? Okay, I need some operators. What are the operators? So you can have an operator which is pick up. You can have an operator which is put down. Right? And this takes some arguments, right? So these will have some arguments like X and Y. I won't specify them. So then what do I have to do? If you think about this plan, it's a kind of trivial plan. I pick up B, I put down B on C, then I pick up A, and then I put down A on top of B. These are some steps which are involve pick up and put down, and I will assemble the tower. Now, of course, I could have some initial condition, and I could have an initial condition where block A is on top of block B, and C is there. Now, in fact, in order to achieve that goal, first what I have to do is to remove A from on top of B. So I have to take a step which is going in the wrong direction, then move B on top of C, and then move A on top of B. I mean, it's like a standard programming exercise of the towers of Hanoi, where you have to do this sort of stuff. Anyway, you get the flavor. So what they had was logical operators, which had some preconditions, and then some add list and delete list. Add list are what are facts that will be true after the operator has been executed, and delete list will be what facts are no longer true. And everything is specified using logic. Okay, and then, so what is the planning process? The planning process is you have some initial state. So it fits into this mode of world model and states and so on, right? There's a state, there's an initial state, and then you have a series of this application of these operators, pick up and put down, with different arguments. And then you get to an end state where we have the following characterization on AB and on BC and on C table. Okay, this is how many years ago? This is like 55 years ago, right? Okay, and then this area has built up. There's the AI planning community, which is broader than robotics. I mean, you can talk about this if you're planning a mission to Mars, right? Or building a factory. I mean, there are many settings where what we have there are tasks and they have dependencies, and you need to do tasks X before you do task Y and so on, right? All of this. If the framework is one which can be, where the operators can be expressed in logic, then this classical paradigm applies. And modern versions of it, there is this language called PDDL, okay, which is for describing plans, and then there is a search involved in finding these plans, but we can do that. I mean, this is all quite tractable. Okay, now let's consider these ideas carried over into robotics. And a very leading example of this is the work from Tomás Lozano Perez and Leslie Kelbling called TAM, which is task and motion planning. So task and motion planning, the task planning part is very much like this old tradition from the logic folks from Shaky and onwards, a very old tradition. Motion planning has to do with the geometry of the world. So if I want to pick up, so this, for the logic people, pick up is an elementary operation, pick up a block. But for a roboticist, this is not a trivial operation, because you have to move the robot arm to the right place. You have to make sure you don't collide with any object. You need to have the right grasp for picking up that object. So this, inside this pickup, is a lot of sort of robotics expertise that is needed. And that's what they captured with this idea of motion planning, where motion planning for them, was usually assuming that you have complete knowledge of the state, and you're really solving this problem of collision avoidance when you have a multiple degree of freedom arm. It's quite reasonable. What are the challenges? So one challenge always is there's always this problem that we have in logic frameworks versus the real world, is because in the real world, we perform actions, but things go slightly wrong. The state is continuous in nature, and logic frameworks are not very good at handling that. Okay, so that's one problem. The other is that suppose we want to take this idea and want to apply it for general settings, right? I want my robot in my home, and it should be able to do my housework. It should be able to clean the floor. It should be able to tidy the children's bedroom. It should be able to cook meals. It should be able to do laundry, fold laundry, etc., etc. Okay, what's the challenge that you see here? The challenge here is we have to design all these operators, right? Designing all these operators, and how many of them are there? Are there a list of 50? Is this a list of 100? Is this a list of 1,000? It's actually an open world. It's unbounded. So this is where I think language models come in, because language models have a lot of implicit knowledge of the world that they have acquired through this simple task of next token prediction. So inside GPT-3 or GPT-4, you actually have knowledge of all these operators, right? They are there. I mean, so I gave an example of making an omelet. Somewhere in there, it would have read some recipe books and so forth. So therefore, it has knowledge of, okay, you must break an egg and you must stir it and you must do this and you must do that. Kind of knowledge is there in LLMs, right? So knowledge of operators is there in the LLMs, and we can draw on it, and we should draw on it. So there's a simple, good way to think about that. What's missing? What's missing often is that these models are not necessarily very good at logical reasoning. They're making good guesses, but they're not good at logical reasoning. So they can come up with plans which are actually incorrect. But if we found ways of combining the LLM type machinery with sort of the more logical inference type machinery, we would have the best of both worlds. This isn't there yet, but it will be there sooner or later. I think one instantiation of this idea is the idea of outputting a program and then executing the program, because your LLM can output a program. So a program is really the same as a plan. There's not much of a difference between plans and plans. I mean, I talked about a plan with operators, but if you think about a program that you write in a programming language like C or Pascal or Python or whatever, I mean, you have operations, right? Each statement is an operation. They have arguments. It's really the same thing as like the pickup operator. So it's the same game. So therefore, the realization has to be that if you are outputting a program, you're outputting a plan. And now what you want to do is some kind of checking. Is this correct? Is this executable, and so on? And then we might imagine a more logic type machinery for that part. So I want to leave it at that and not get too hung up on the current usage of these LLMs, because often they are not necessarily used the right way. But in the long run, there will be a role for LLMs, and they will be in providing operators. And we will need some process. Maybe the LLMs the error rates will come down enough that you don't need to check, but very likely you may need to check. So let me pause here and ask if you have any questions on this. Okay. And now what is language not good for? Okay. I have a couple of slides which I want to argue that language is not good for certain things. And this is essentially to do with the role of how much spatial reasoning is present in LLMs. So this is a paper from some colleagues at Apple. You can find this on arXiv. I like this paper a lot. And I want to give a context for it, which is a couple of years ago, we had at like one of the CVPIs, there was some debate and the other, and And at that time, Vladlen Colton was very excited by LLMs and very much in the mode that, I mean, computer vision and robotics can all be solved by LLMs, and they will, or they, I mean, that may be an exaggeration. And in fact, part of the the claim comes from the following, which is a legitimate argument, that these LLMs are bringing in a lot of knowledge of the world through the words. So the claim would be, you build a word model, but you've implicitly got a world model for free. That would be the thesis. And as such, it's a plausible claim. So now you have to test it. And the way you can test it is by various kinds of spatial reasoning tasks. So there are a bunch of spatial reasoning tasks which come from the psychologists. So these are the kinds of tests which show up in, IQ tests and so forth. So for example, there is some object and you have to rotate it and guess how it looks like from another viewpoint. There is some maze and you have to find a path from the start to the end and so on and so forth. And what we can do is to try some kind of VLM. I mean, this has to be a model which can take in pixels as input and see how good they are at this. And they did a bunch of these tasks, and they tried a variety of these models, GPT-4o, GPT-4v, et cetera. And these were multiple choice questions, and the chance performance was 25%, and most of the models were like close to chance. And humans are very good at it. So at least current models have not solved the problem of spatial cognition. And they had two versions of it: spatial reasoning in the large and spatial reasoning in the small. Small is more about like rotating objects and guessing how they are from different points of view. Large is more like, okay, I am at a certain position. There's some other person who's sitting northwest of me at 7 meters. There's some other person who's sitting southeast, south, or just south of that person at 12 meters. What's the orientation of that person with respect to me? Things like that, right? Which is very easy reasoning with geometry of the type that any high school kid knows, right? And even if they haven't studied it in geometry, they can just answer this from their intuitive spatial reasoning, but these models can't. So that's sort of an argument. Eventually, whether we will have multimodal LLMs which will be able to answer this, I hope so, but they will come when we have treated the spatial reasoning part of the problem with due respect. I think the current models are largely language models with a little bit of vision thrown in, and usually that vision part is basically that they have recognition of you recognize the scene, and now you've got tokens corresponding to the objects, and so there's like a bag of words model. And people are pushing this technology. They are trying to put in more spatial information, but it's fair to say that it isn't quite there yet. But a few years down the road, where that branch of adding in spatial information into these models, as it advances, we might do better. That's totally okay. And then I want to conclude with this story. So these are instructions on how to climb a staircase. Okay. Let me move this out so you can. Okay. Let me put it here so it doesn't bother you. So I'll let you enjoy reading this for a few minutes. It's from this author called Julio Cortázar. Okay. So this is how you teach a person how to climb a staircase. Okay, and if this is how you try to teach your 3-year-old child how to climb a staircase, I don't think you will have much luck. It is much better to do this. As I said, you can talk about climbing a staircase, or you can climb a staircase. Okay, and my point is, climbing a staircase is easier than trying to pass those set of words. So, okay, so but So I usually use this as a line mainly to win arguments against the people who are big fans of LLMs, that language is not quite the right way to capture skills. I mean, we have low-level robotic skills like picking up, throwing, walking, climbing. And these skills are in the space of joint angles and movements of joint angles and perception from pixels and so on. And that is needed, okay? And words that don't capture that. But I don't want you to make the other mistake, which is to say that words are unimportant. Words are important. Words are important for capturing high-level goals and plans, right? Like, why did this robot want to go climb the staircase, right? Things like that, right? I mean, I think those are equally important, and we need to have this balanced view. Okay, I'll stop here, and I think we can. If there are any questions.